Yeah, he got that thing. It broke off. Oh my god. EMAG. I went to RC submarine.
Just talk to you straightforward about this. Now, I don't know what really your study habits are or anything like that, how you go about preparing. But I'm going to give you just, I'm saying this sincerely, I'm trying to help. I recommend between classes, you do the homework. It may take, I recommend at least 2 hours between classes. Do the homework, go over it. I'm going to warn you about this class because a lot of people flunk it. This is the one thing you can do. If you do this, I'm almost guaranteeing you're going to get at least a B, probably an A. Between every class, spend 2 to 3 hours. Just do the homework. I'll give you more homework, more difficult problems. Do it. If you don't understand something, see me. But don't get behind in this class. Now, the D field stuff on the last problem I'm going to go over, the D field was an almost gimme kind of thing. You get the E field from that, then you got the voltage. It wasn't meant to be hard. But people are like, I think, studying old tests, old quizzes. Oh, he'll ask this, that, and the other thing, instead of understanding the material. If you do that, I'm just level, you're probably going to kill yourself at the end of the day.
Okay.
I'm trying to just be honest with you. You don't want to do that. You want to know the material. Don't remember a problem. Oh, that's how we did this problem in class. Make sure you know the material. I'm just leveling you. You're not going to see my old tests. You're not going to see my old problems. You're going to see stuff related to the homework. Y'all follow me in this class? I'm just guessing on that one. I think I'm right. And this class does get harder. I mean, more complicated. If you stay up with it, it'll all come together. It's easy. But don't. What's your phone's favorite or yes?
I think it's, I rather have it on the chair just.
Well, I'm just thinking if it's standing upright, it probably has a better chance of catching sound. But I don't know.
Okay.
Just thought.
Alright.
All right,
Yeah.
alright, that said,
Yeah.
first thing I want to do
Can I
is,
use this thing?
He has a
what?
You can come on up this side, Doug.
Look, if you want to go ahead and orient me. What I want to do is just go over this quiz in basic form, because this is a basic Gauss law problem. I even gave you a problem almost identical to find the D field like that, and I did part of this on the board if you look at the old lecture. All right, this is not supposed to be a difficult problem. And but I give you a hint, like I like these problems with variable charge densities. You kind of read between the lines. I'm probably going to give you a problem on that. Don't think I won't. Okay. So that said, let's go through this problem. I'm going to just do this in terms of generalities. If you had a bad day or whatever, I mean, I guess how many had this test in digit? Well, I don't know how bad it was. I mean, Dr. News, in my opinion, one of the best teachers there is, but his tests may not be reflective of what you thought was coming. And that's unfortunately the truth in a lot of, the higher up, you see, at the senior level courses, you have to really know material, because depending on who you get, you can really get ambushed. If you're just studying like old tests, this point, this point, this point, that's it. But we don't need to know the others. Boy, you can fall, it can really hurt you. Anyway, for this problem, here's the deal. I got a charge, this is spherical charge density. I've got a radius A here, and inside here I have a charge density. And I'm just going to call it rho naught over R, but it can have any form at all. Now it was nanocoulombs, it was really 4 over R, nanocoulombs per meter. Should have been per meter cubed, it was per meter squared. So I gave a lot of leeway. I gave a whole lot of extra points because if you read it that way and assume that, I gave you full credit if you did it right. Here, this should have been coulombs per meter cubed. Then you could put the 10 to the minus 9th into the rho naught. Y'all follow me? Rho naught could be 4 times 10 to the minus 9. How many understand it? At least that part. You got me on this, class? We're going to do it this way. So if we have this, the first thing we need to do is find the D field. So for the first part, I'm going to say for the radial vector R less than A. Now I'm out at this distance, and I put my Gaussian surface here. All right, that's the Gaussian surface. And remember, the D field is going to be radially outward. Do y'all see the sphere? It's spherically symmetric, right? It wasn't a cylinder, it's a sphere. Y'all follow me? All right, so if we go ahead and use Gauss's law, this is what I look for when I'm grading. I want to see a statement about Gauss's law. Not a lot of scribbling. D equal bunch. I don't understand what you're talking about. So the integral of d dot ds over the closed surface is equal to the charge enclosed. If we're inside R equal A, it's going to be an integral. Really, it's a triple integral of rho v dv. I'm just going to leave it like this to show the general form. Now, I look for this when I grade. So I know that's the starting point. It's Gauss's law. You all with me? This is, you could do it if you want, but this is just the surface area of a sphere times d. How many understand that? You all with me on this? That's all it is. The surface area is 4 pi r squared times d of r. That's all it is. With me? Now on the other side, I gave you the differential volume. Here we go ahead and I'm going to put the triple integral, put the limits. Rho v is rho naught over r. That's the charge density. This is volumetric. It's supposed to be volumetric. You all with me? Now I got to put the differential surface in. That's r squared sine theta. And this I'm going to go d theta, d phi, dr. And theta goes from 0 to pi. Phi goes from 0 to 2 pi. And finally, r, and technically I should prime these right here. R goes from 0 to r here. You all follow? I'm just setting it up the way, and a lot of people actually set that part up right. You all with me, class? Now, when I come over here, I know d of r, right here, is going to be 1 over 4 pi r squared. This is the 4 pi r squared I took over there. You all with me? Can you all see this, class? Go back. I'm just trying to go ahead and manipulate this, and it's not difficult to do. Now, over here, I'm going to manipulate this integral. Rho naught can come right out in front. You all agree with that? I saw this written, and then here's what people did. They literally took rho naught over r out in front. I didn't understand that. It's a function of r. You all follow me? You have to do the integration with r inside the integral. So I'm going to take rho naught out in front. Now, when I integrate sine theta, I get minus cosine theta. When I evaluate that from 0 to pi, I get 2. Y'all with me? Then when I integrate d phi and I go from 0 to 2 pi, I get 2 pi. It's 4 pi for those two angular integrals. Finally, I see that this r cancels one of these. Y'all with me, class? I'm just trying to show you exactly how you go about this. Y'all with this? Now, r dr is r squared over 2. Y'all follow me? And you're evaluating from 0 to r, so it's simply going to be r squared over 2. This is the entirety of the integral that you need to take care of if you're at r less than a. How many see this right? You okay with it? Now, obviously, you can see the 4 pi's cancel. And you see the r squareds cancel too. I mean, I did this on purpose because that way the E field's constant. It's a trivial integration when we get the voltage. Y'all with me? I made sure it was as easy as possible. So this means the r squareds cancel, and that's simply rho naught over over 2, rho naught over 2, and it's in the AR direction. And that's the D field for R less than A. Everybody with me? Let me understand this. Now you're going to get another problem like this. It may be in cylindrical coordinates, it may be in spherical, where the actual charge density will vary with radial distance. You hear me? Could be spherical, could be cylindrical. But I want to make sure you can handle the problem. After that, since the first part, now that's the D field. So the second part, and by the way, to get D field, we divide by epsilon naught. That's the only thing we're going to do in a second. All right? Now, to get the second part, now I'm going to be for R greater than A. All right? What's this going to be? Well, again, when you're doing these problems on quizzes or tests, State the law you're going to use. Don't scribble stuff like D equals 5. That doesn't make a bit of difference to me. I don't understand why you even put that there. It may be right, but I don't understand how you achieve that result. Follow me? So when I'm grading, I want to see Gauss's law. That's Gauss's law on one side is equal to the charge enclosed. Here, you can just say Q enclosed if you want. Or you can do the actual integral of the charge density, but limit it to A. You all follow me, class? And I'm going to do this in a second. How many understand that right there? I'm not chastising. I'm trying to encourage you. I was a little bummed grading it because I was hoping people do a whole lot better. Only a handful of people got over it. Only, I think, 110, maybe a couple of 9s, but not many. You all with me? So I'm trying to make sure you can handle stuff like this, because this is typical. All right, now, if you look at this, this is again the surface area. It's always going to be the surface area times the d field, if you can use Gauss's law. With me? So this is 4 pi r squared dr. Now on this side, now all the charge, you're outside the region where the charge exists, so we have to find the total charge. Do you agree with this? So we take that same integral we did before, and it's rho naught over r, then it's going to be equal to r squared sine theta d phi dr. And technically I got to prime the r. Theta goes from 0 to pi, phi goes from 0 to 2 pi, and r goes from 0 to r. So it's the same exact form as the last integral, except I put an r down there, and it should have been an a. Y'all follow me? And the reason why? Because the charge density beyond that is 0, correct? So you only have to integrate out to a. You can integrate further than that, but it'd be a separate integral, it'd be 0 integrated. Y'all follow me? Let me see your hands. Do you understand this right here? There shouldn't be any mystery about this. Okay, over here I get d of r equal to 1 over 4 pi r squared. Now over here, you know I'm going to get the 4 pi, right, from the angular end. Yes, sir?
Why wouldn't it be from integrating from a instead of a from 0 to a, like r to a?
Remember what Gauss's law says, it's the integral of everything inside that surface, closed surface. Everything inside that surface starts at the origin and goes to the point, the radial distance. Everything inside the sphere. It's all the charge. Y'all follow me? But ask any questions you have. Usually there's something small that confuses people. It's usually not big. You can usually understand how actually execute an integral if you can write it properly. Most of you can. All right, over here, that's the 4 pi. And again, then I have rho 0 out here. Right? Now I got my what? That r cancels that out. I have r dr, you get r squared over 2, but now it's evaluated from 0 to a. Y'all with me? So it's going to be a squared over 2. And you can see the 4 pi's cancel, right? So you get this d of r equal to, and you can do it a couple of different ways. I'll just call it rho 0 a squared over 2. You can make that a constant if you want, over 1 over r squared ar. That's the second part of that problem, where I should say the part of finding the d field in both regions. Y'all with me? Now graph it. You're going to have to be able to sketch things accurately. And in jobs, now, you can't do this with digital circuits very easy, but if you're doing a lot of different things in engineering, especially if you're out there with antennas and stuff like this, you're going to have to be able to sketch in some way, shape, or form the expected response of the system. Usually, just estimate. So this is sketching the d field. If you look at this, here's the radial distance r. I'm calling this a. And if you look at this, the d field for 0 to a is just a constant. Y'all follow me on this? So it's just simply, if this is the d field, it's a constant, and it's rho 0 over 2. You can put the 4 nanocoulomb over 2, so it'd be 2 nanocoulomb. All right, y'all with me, class? Per meter squared? That's it. Constant, out to A. And when I hit A, now it's going to start dropping as 1 over r squared here. Y'all see that, class? So it's going to drop And it'll go like this. That's it for the first part. How many understand this? How many understand the mistake you made if you made a mistake on this part? I'm going to bet money it had to do with this right here. Because I graded those things and I've seen a whole bunch of convoluted things. I didn't understand what you're trying to do. And I'm just trying to be clear about this. This is the way you do this. Start by always stating Gauss's law and methodically going through the steps. Y'all with me? I hope you can understand this. I don't think the next time you see us, you're going to have trouble. But again, I don't know. I'm just trying to make sure about it. All right. So we got the D field. Now we're going to get the E field. Y'all with me? Now, after this point, the voltage becomes fairly easy. If you got the E field, it's a simple integral. Y'all agree with this? Let me do it right here. And I said the voltage at infinity equals 0. Didn't that class? Isn't that problem? All right. So now we're going to do this. We're going to start with finding the voltage for R greater than A, right? And I'm going to just state what it is. So the voltage between any 2 points, and I'm going to write it this way for a reason, VB minus VA is equal to an integral minus A to B of E dot dl. Do y'all agree with that? I'm just stating this explicitly the way it's in Dr. Wentworth's book. Do y'all follow me? Now I'm going to change one thing. I know A here will be at infinity. Do y'all follow me? So if A is at infinity, I define VA as 0. Didn't I, class? It doesn't have to be, but I did. So I can erase that. Down here, I can just say at infinity. You can say as A goes to infinity if you want, or R goes to infinity. Y'all follow me, class? Everybody with me on this one? All right, now execute the integral. Here, it's this, right? So the E field would be what? Let me put it right here so you can see it. As a matter of fact, why don't we do this instead of B, we can just call this R, right? Because that's going to be the point of observation. Do you agree with this, class? I'm just going to call it R, so I'm not going to change it. So that's how I'm integrating from infinity to that. So what's this going to be? Well, that I have to divide by epsilon naught. Does everybody see that? So it's rho naught A squared over 2 over 2 epsilon naught. It's in the AR direction. I'm going to integrate AR dr, right? Correct? That integral right here, I forgot the R here, because it's an R squared. When you do this integral, the AR dot AR goes to 1. Then I integrate it, right? And I'm going to get minus 1 over R, but there's a minus sign, so it becomes a plus value. Do you all agree with this, class? So this whole thing becomes simply what? Rho 0 A squared over 2 epsilon naught. And then it's simply going to be 1 over R. Right? Now that is the same thing as taking the total charge inside that sphere and dividing it by 4 pi epsilon naught R squared. Y'all, epsilon naught R. Y'all follow me in this? Some of you got that. I was very happy to see that. Some of you, I think you were desperate. You got confused. You didn't know which way to go. You weren't expecting that type of problem. This type of problem is going to occur over and over again, where I use stuff that I taught before to get values you need for the next one. Like the E field you get from the D field. The E field you need to get the voltage. Y'all with me? How many see it so far? If you find mistakes, that's the main. Now, when I look at, now I'm inside the sphere, right? Y'all see this, guys? That E field is constant. isn't it? So that means the voltage from that point on, you're gonna take this voltage right here and evaluate it today. Let me do it over here. And you're simply gonna go ahead and find the additional voltage you get between the outer radius of the sphere, or A, and the inner part, R. So now if you're talking about, this voltage is for R less than or equal to A. Now if you're for R greater than or equal to A, for R less than A, now remember technically the voltage V of R was equal to that integral from minus infinity with a minus sign to R of E dot dl. I'm just going to make this point, right? When we go from infinity all the way to A, we're going to get a singular value. Do you all follow me on that? So you can break this up and say that this is going to be simply this voltage evaluated at A, so it's going to be rho naught A squared over 2 epsilon naught, and then you put A in here. I'm going to leave A there. That's simply the voltage at A, right? Now we have to add to it what? You're going to have to add to it, and it's really going to be the integral, and you can put a minus sign if you want, but this is going to be the integral of the E field right here. And technically, I guess I should put a minus sign. And this will go from A to R, AR dot AR dr. Let me just make a comment on this. I did it the same way. This is a voltage. It starts at A. Yeah. It goes to R, because now R is less than A. We're inside there. This is going to be the additional voltage you get. Do y'all follow me? Can you see it in the far back? Now, the way I do these things, whenever I see something with a minus sign, and I got limits, I change the limits. Make it plus. That's all I do. It's the same thing. Y'all follow me? Everybody good with that? So what is that going to be? That's a constant. AR dot AR is 1. The integral of dr is R, evaluated from A to R. Y'all follow me? It's going to be what? Rho naught over 2 epsilon naught, and it's going to be A minus R. And that's the voltage inside. So what's the maximum voltage? Just look at it and think. What is your gut say? At 0, right? What's the maximum value of voltage going to be? That right there. You'll notice that A and that A cancel, right? So I have rho naught A over 2 epsilon naught, rho naught A over 2 epsilon naught. Y'all follow me? Or it's just rho naught A over epsilon naught is the maximum voltage. How many understand it? You okay with this? If you messed up, put it behind you. Just realize what you need to do. All right, today, first, are there any questions about the resistance homework? I'm going to do a problem, but I have to make sure I answer any questions. Anything? All right. You're probably feeling down. You had another test today. Sounds like things didn't go so well. I encourage you. I mean, you guys, you have the intelligence, believe me, all of you are, but sometimes you just have to discipline yourself to spend the time doing this stuff and really understand. It's very hard at times with all the distractions. Now we have Georgia. This game always causes disruption. Every year I've ever taught, this game was a singular point. I mean, Alabama's bad, but this particular one, I don't know what it is about this, but kids, if I ask you to do some homework over the weekend, if I get half the class doing it, it's a miracle. You know, there's a history of this Georgia game. Does anybody know? No. What? Long ago, I guess before every one of you were born, there was a huge fight out there on the turf because they try to rip up the actual turf. Does anybody know about this? They turn the fire hoses on. You do. All right. I think that's the genesis of some of the reasons all the students in the past I've had during the Georgia game, if I assigned homework, even extra credit or anything, if I got 50% of them doing it, it was an act of God. This game, I think everybody and his brother comes in for it. I have not had anybody hit me up to crash in my pad, thankfully. But I don't know if you guys get this anymore. But everybody's my best friend. And we just need a little time just to crash, and that's always bad. All right, so how many tried the problem? You had another test. If anybody did, I'd be surprised. Anybody? Jonathan? Not even you? Karina, you didn't do it either? Shame on you.
I'm sorry.
We're gonna do a few. Do me a favor, give me your attention so I can probably help you a great deal because this is coming up in the next quiz. All right? When's the next quiz? I'll tell you that when I'm done. All right? Pay attention. Ready? We're going to do this, but we're going to do resistance. I'm going to do resistance first with spherical coordinates, and I want to make sure everybody can handle this based on the way I taught it. First, in general, if you want to find resistance, you assume something. Usually you assume a current, so I'm putting it down. After you assume a current, you get the current density. This is the way we do this. Y'all with me? Sort of like Gauss's law. Assume a charge, get the charge density, right? Or get the value of D. Y'all follow me? After that, you get the E field. E field is simply equal, matter of fact, I better put this here. J is simply I over the area. That's all it is. And it would be in a vector direction, the normal vector direction to the E field. I'm putting it this way in a general sense, but I'll apply it and make sense of it. Y'all with me, class? Doesn't matter what the area is. It could be a cylindrical, could be spherical, but it has to be something where the current is uniformly distributing itself, either in spherical or cylindrical coordinates. Y'all with me? Or even planar coordinates. After you have J, you get E. E is simply going to be J over sigma. Y'all with me? Remember, J is sigma E, correct, class? After you have that, the last step is you get the value of the voltage by integrating E dot dl. I'm being a little casual. I don't care about the minus sign in front of there. As long as you integrate over the extent of the resistor, it's always going to be a positive voltage. It's always going to be a positive current. Y'all hear me? So you mess up the minus sign, get rid of it. It doesn't belong. All right, now, we're going to do the same exact shape of problem that you did, only in spherical coordinates with resistance. Now, this problem, I give this problem, hint, I give this problem, this type of problem, every single time I teach this. It's either going to be in spherical or cylindrical, and it's going to have a variable conductivity. The conductivity would be a function of radial distance. Now, you can take that to the bank, just so you know it's coming. All right, this is not going to be one of those things he might give it. He's going to give it. And it can't be clearer than that. All right, so here's the problem. Now, we're going to have a hollow sphere of radius A, outer radius B, and this is going to be a function of R. Y'all with me? This is where the conductivity is in the outer region between A and B. It's a hollow, it's a cylindrical or spherical resistor. I think we're being droned. Now, what we do is this. This is assumed metallized on the inside. You just think of it this way. I try to give you a visual tool to see this. Assume you got a battery here, and the entire outer surface of the sphere is grounded. The inner surface is a conductor, all right? So you fill that stuff with some material that's got a conductivity. We'll assume the conductivity is sigma. I don't know what sigma is. It could be a function of rho, the radial distance, but it's going to have a value nonetheless. Y'all with me? Now here's how you start this problem. First, you assume, say this is plus to minus V. We're going to assume there's some current I going in there. We're assuming that. Got me? It'll eventually go away. After we assume I, we get J. Well, I could write the equation, the integral of J dot ds is the I, or the current penetrating surface, but by now I think you can handle this. Let me see if I can actually show this. So, if I come out any distance r, and I put a surface around there, if the current's flowing from the inner to the outer electrode, right? Can you all see the current density is radially outward? How many can see that? It will be symmetric. So if you want the current density at a distance r, you simply take the total current I and divide it by the surface area, 4 pi r squared. You got me on that? That's the surface area of a sphere. How many do it? With me? Yeah. Okay. So that's simply going to be I over 4 pi r squared AR. Now, if that was cylindrical symmetry and we had an inner radius and an outer radius, then the surface area would be 2 pi rho times the height. Y'all follow me? That's the only difference as far as the technique you would use. Got me? Over here, once I have J, now I need E. What do? Look at it. Divide by, you all see this? What's that term? What's that called? Sigma. Divide by sigma, right? So you get the E field, and I have a comment here. I take I over 4 pi r squared sigma AR. Now, in your notes, star this point. Put a star there, because some people are going to study and cram, and they're going to say, oh, I got this. This can be a function of R. In other words, just like my charge density was a function of R, this could be a function of R. So the integrals aren't always going to be just 1 over R for the voltage. You got me on this? You don't know what they look like until you do the integration. Okay, good, you're kind of. All right, now, I don't know what it is. If we assume it's a constant, that'd be we can do it that way. If we assume this is a constant, sigma naught, but it usually isn't, if on my test, then the next thing we're going to do, running out of room here, we need the voltage. You all with me? So to get the voltage, what do? Well, I integrate from the inner radius A to the outer radius B, and I don't care about the sign here because it's going to be positive no matter what. Y'all follow me? It's going to be this, which is I over 4 pi r squared sigma AR dot AR dr. I want the voltage. So if you look at this, this is going to be I over 4 pi sigma. Integration of what? AR that AR cancels, right? Goes to 1. We get 1 over r squared. Integration is simply minus, yes sir?
Oh, maybe I missed it, but is there a reason there's no negative in front of the interval?
We can put a negative there and put VB minus VA there. But here's the point I was trying to make earlier. It doesn't matter if it becomes negative because the resistance is strict positive. When we divide that by I, ignore the negatives. I'm trying to give you just a piece of advice because a negative resistance tells me you don't know what you do. I mean, and I see this. I really do. All right. So now we get a 1 over R, so it's really going to be 1 over A minus 1 over B. The assumption here is A is less than B. Sorry, what? Hey, don't worry about it. Y'all with me, class? Give me a shot here. Do you see this? We're assuming A is less than B. That's positive, right? How do I get the resistance? Voltage divided by current. I don't want to make a mistake. Sometimes I feel that way in front of you too. I'm thinking, how am I going to phrase this so you understand? Well, I don't know. All right. Divide by I. That goes away. And then you can forget that. This is the resistance between the inner and outer conductor. Y'all follow me? That's spherical, right? Now, be attentive here. I want to do this one time here to make sure I got everybody's attention. Going back to this stuff. If it's spherical, this is always true if it's spherical. You got that? This will always be the current density, period. Got me on that? Now, to get the E field, you got to divide it by sigma. Suppose I make sigma a function of distance. Y'all hear me? Suppose I make sigma a 1 over, say it's sigma naught over r. So then you would put sigma naught over r in here. Y'all follow? It can be anything. It can be sigma naught times r. Y'all with me? It can be any function of r I want. It has to be a function of r. If it's a function of theta or phi, it will not work. It has to be spherically symmetric. So if I have this, what is the E field effectively? Well, it's really going to be equal to I over 4 pi sigma naught, but then it's just divided by RAR. Now it's just 1 over r, not 1 over r squared. Got me? Now what's the voltage between A and B, or B and A? You can almost do this in your head. It's going to be what? The integral I over 4 pi epsilon naught, 1 over r, AR dot AR dr. Well, I over 4 pi epsilon naught, and hold it, I forgot the sigma naught, not epsilon naught, sigma naught, my bad. And then it's going to be the natural log of the outer radius B over the inner radius A. Y'all with me? Y'all follow me? Integral of 1 over r is natural log, right? You got to make sure you know this. 1 over x dx integrates to natural log. 1 over x squared dx is minus 1 over x. You have to know these integrals. All right, now, if I want the resistance, what do? That's the voltage. What do? I got, no. Divide by the current, right? Just get rid of the current. Y'all with me? Yeah.
Is that VB minus V?
VA, it doesn't matter what it looks like. It's just the voltage difference. The only thing I'm trying to indicate is that's the voltage difference between the inner and outer. That's it. All right, now, it's going to be positive. Trust me. So if I divide that by current, that's the resistance, right? Y'all see how many different types of problems can happen if I change sigma. It can come out in a bizarre way. Suppose I make sigma r squared. Then you have a 1 over r to the 4th integral, right? So how to do that kind of integral? You should know. I mean, you guys had calculus. You've done this stuff for a long time. Okay, I want to make that clear. With me? Let me say this. We'll do one with. Actually, you think you can handle cylinders? Let's see. Oh. What's a cylinder?
It's a cube, obviously.
Oh, cylinder is, it's got a final answer.
Natural log. Ln. This is natural log, Ln. Now, if I want to just say this, because this happens. In mathematics, sometimes they don't have Ln. They use log. If it doesn't have the subscript 10, all right, it's assumed natural log. In MATLAB, log of a number is actually going to be the natural log. Log 10 is log base 10. Y'all hear me? So just remember this if you're looking online at supplementary material. That can be confusing. I don't like that difference, but it's out there and you just got to live with it. When I put natural log, it's ln. I don't type log without a subscript, so just so you know. Okay, We'll do a cylinder. You'll do a cylinder. You're going to tell me how to do it. I want the resistance per meter between the inner conductor on a cylinder. This is going to be per meter, so assume it's infinitely long. You can put it on the z-axis. Call this inner radius A. Remember, this is cylindrical coordinates. Then I'm going to have another cylinder that this thing is inside of. And this is going to have a radius of B. And then between A and B, I'm going to put a conductivity. Remember, the conductivity can be a function of the radial distance. The radial distance would be rho. It's measured from the z-axis, point of observation of either the J or E or D or whatever. You all with me?
We're trying to find the, what was it again?
Resistance.
No, of the inner cylinders that you said?
No, resistance is always between two surfaces. It would look like this.
Sorry.
R, call it AB. Y'all with me? If you wanted a lumped element, this would be per meter, by the way, a lumped element value of the resistance that would occur between inner and outer conductor. And assume that the inner surface is metallized and the outer surface is metallized. So here, that's all metal and that's all metal, right? Now, when we have current and we put current inside here, doesn't matter how it gets there. Assume you have a battery. And assume the outer conductor is metallized. You get the idea. And there's V. You can make the height of this 1 because I'm going to talk about the resistance of this per meter. You all with me, class?
Is that like a coax cable?
Oh, yeah, it is. But it's just a single 1 meter chunk. Yeah, exactly. It's a coaxial cable, interconductor. Most coax cables, you're used to have a solid piece of copper in the center of a certain radius. Then there's an outer, it's a woven aluminum, typically aluminum sheath on the outside of a given radius. So, but the reason I don't like, see, coax has an extremely high resistance per meter because it's a dielectric. It's not something that's meant to conduct current. So these type of resistors are used, and I actually published a paper about something happening with these type that I want to get into right now. Anyway, it's a cylindrical resistor like this, okay? Per meter we want. So if we think about this, we always start with I. We're going to assume you have I, and if I look at this thing like right down the z-axis, you see this. Here's the material right here. And now I want to find, at a distance rho, I want to find my current density J. Do y'all follow me? I'm between A and B. Everybody follow the concept. So how do I get it? Well, I know that J itself is going to be related to the current. This is per meter, by the way. Remember, 1 meter section or 1 unit section. Current I. And now what's the area of a cylinder surface like that? Think of the label on a soup can. It's always the perimeter or circumference, 2 pi rho, times the height. You all follow me? What do I always make the height? And you should too. So I can say that this is just divided by 2 pi rho A rho. Got me on that? After that, what's the next step? I got I, got J. What do I need next? E. Well, you're way ahead of me, but voltage is something we get. We need the E field, don't we, class? How many understand that? So we divide this by sigma. We get the E field. And we're going to say the E field is simply equal to J divided by sigma. I'll make sigma constant here. But remember, in general, sigma can be a function of rho, so you have to go through this part. So I'll just make it a constant for this one, just call it sigma naught, but we can change that. So this means it's just sigma naught. So it's really I over 2 pi sigma naught rho in the A rho direction. With me? Now I want to get, you said it, voltage. the V word. So now I say the voltage is going to be equal to the integral of E dot dl, right? Normally, it's minus from A to B, but honestly, the negative sign is of no use here because we want only magnitude. So it becomes the integral of that, which is I over 2 pi sigma naught rho, A rho, then it's dot A rho, D rho. And here, you can flip the values here, so it's going to go from really A to B, and that's going to be I over 2 pi sigma naught. What's integral of 1 over rho, class?
Natural log.
Natural log. From B to A, right? And if that's the voltage, how do I get the resistance, class? Got it. I know I did. And yes, and that's the resistance. That's a classic problem. In these problems I like, but that value of sigma ain't going to be a constant. So memorizing that answer does you absolutely no good. Hear me? All right. Now, if you have a question, I hand somebody. Yes.
So in Whitworth's book, it does it solves for V or voltage before solving for the current.
No, he's talking about planar system, right? We can do that one. He has a parallel plate now. You'd never
I
do
didn't
it.
get the parallel plate.
It is. All right, so we can do this one.
Spherical shell ones.
No, he doesn't do that. If he does, he did it bad. No, you're talking about capacitance or resistance.
It wants to find the resistance. It started with
A sphere?
2 spherical shells.
No,
Radius.
don't do it that way. You're going to waste time because if you have a voltage difference, how do you get the E field from that?
Well, like it starts with the E field, then goes the voltage, then goes.
All right. To get the E field, what do you need?
It just.
You got to have J. Trust me, don't worry about
It
that.
goes
Let me
with
go
the
ahead and just tell you the way I'm showing you is right. If it's a planar system, I'll do it right now since you open up that can of worms. I was going to wait until I get through capacitance, but I'm going to do it. By the way, how many are going to the game? I hope you don't get sunburned. I can always tell who goes to the game on Monday, usually. I look at the faces and the beet red, yeah. I know where you've been. All right, so since you asked, here's another way to do that problem. Let's assume I got a square or a rectangular surface like so, and between these surfaces is a height h, and these are plates and they have an area A. Got me? So think of an ice cream sandwich. And in here, in between these two things, I have a conductivity sigma naught. It doesn't have to be sigma naught. It could be a function of a position. Got me? You might as well call this, it doesn't matter what it is, they have area A, call this, say, Z. Good? Got me on this? Now, you can do this. You can start and go backwards. We can assume V first. If I assume a voltage from here to here, matter of fact, let me do it this way. From here to here, if I have V naught here, right? Because the actual cross-sectional area is invariant with distance and the conductivity is constant, you hear me on this? You can assume that the electric field will be constant between these two. Do you understand that? And because of that, you can get the electric field from this by simply going ahead and saying V naught divided by the separation distance h would be the electric field, and it would be in the AZ direction. So this would be the electric field, and I'll call it just E electric field. You all follow me? Now we're not after the voltage, we assumed it. After I have the electric field, I need the current density. I'm going backwards. What do I do with the electric field to get the current density? Multiply by sigma. Now I say J is equal to sigma E, right? Is equal to sigma V naught over H AZ. Finally, that's the current density, right? The units of current density are going to be amps per meter squared. Think about this. Now I need the total current be flowing between the plates. I assume a voltage, this is probably a better way to think about it. I've got some voltage, and what I'm looking for is the current I naught. If I have that, I got the resistance, right? How do I get the current? Just think about this. You see how this current density is a constant? It's sigma naught, right? You all see that? Current density times area. It doesn't vary with X, Y, or Z, does it? Just multiply by the area, and you now have what? The current, right? So the current would be that times the area. Just let me finish this. H times A. And that's going to be equal to the current I, right? What's the voltage? You got to invert it, right? And then divide by the voltage. So if I invert this thing, I get the resistance here between top and bottom is going to be H, right? Divided by sigma naught and A. And by the way, that is the resistance of any kind of material, constant cross section, constant conductivity between one end and the other. It's proportional to the actual length of the material that the material exists in. It's inversely proportional to the cross-sectional area the current flows through, and it's inversely proportional to sigma. Y'all with me? I'm going to give you some more homework. On Monday, we're going to go through capacitance. Your quiz won't be on Monday. I'll decide when the next quiz is on Monday based on the turnout and the responses to my inquiry. John, Stephen, I hope I made sense of myself out there. Absolutely. Let me just erase this. Thank you very much. Do you have a class right now? All right. I don't know if there's a class in the